Section 7.4 continues with confidence intervals, though it tends to be the trickiest section in the chapter. We're no longer using a Z distribution in the Z table with this section. Instead, we're using something called a T distribution, a T table, and it's because we don't know the standard deviation of the population. In this section, we'll only know the standard deviation of our sample. So to use a Z table, we either need to be working with a problem about categorical data and finding a confidence interval for proportions. If we're working with quantitative data and making a confidence interval for means, we need to know the standard deviation of the population. Okay? Normally, we don't know that. We only have a sample, we have a mean from that sample, and we also have the standard deviation from that sample. Okay? It's rare that we know the standard deviation of an entire population, because if we did, we would probably also know the mean from the entire population, which would make it pointless to actually create a confidence interval. So in situations where the population from the standard deviation is unknown, we use a new distribution. It's called a T distribution, and it's very similar to a Z distribution. So this blue curve here is the standard normal distribution. It's what we've been using with our Z table. It's the one you're familiar with. These other two are both T distributions. There's an infinite number of T distributions. You can see they look the same with the exception that there's a little bit of extra area in the tails. Okay? As our sample size increases, our T distribution gets closer and closer to the normal distribution. So there's different T distributions with every sample size, and it's based on something called degrees of freedom. And the degrees of freedom is given by this equation down at the bottom here, n-1. As the sample size gets bigger, it gets closer and closer to the normal distribution. With an infinite sample size, it would match the normal distribution exactly. The T distribution is centered at 0, just like the normal distribution was, but the standard deviation is no longer 1. It's now something different. So how does this change our confidence intervals? Well, to start, we're not using a critical Z-score anymore, and instead we're using a critical T-score. Standard deviation becomes something called the standard error. It's the same thing. Instead of a sigma on top, we have an S on top. Standard error is just a standard deviation where we don't know what the actual standard deviation is. Okay, so it's being estimated. Our actual confidence interval equation starts with that point estimate, the sample mean, T-score instead of a Z-score, standard error instead of standard deviation. In order to use this method, we either have to have, we have to have a simple random sample, and then we either have to have a sample from a normally distributed population, or we have to have a sample size that's large enough, meaning that the sample size is greater than or equal to 30. So one of the things I should have given you is a T distribution. Make sure you're on the correct side of the paper because it's only one-sided. The opposite side is a chi-square distribution, which we aren't dealing with yet. So number 1, part A, we want to find the critical T value for a 95% confidence interval where n equals 7. So step 1, we want to find the degrees of freedom. Degrees of freedom is just 7 minus 1. Okay, so it's n minus 1. We get 6 degrees of freedom, right? We see it here. Now 95% confidence interval. You can see confidence intervals at the top here. All right, we can go over to the 95%, and we're going to just intersect these two rows and columns here. So the critical T-score is 2.447. All right, so if we were to continue this, okay, and let's say we went to a sample size of 81. As the sample size grows, the T distribution gets closer and closer to a normal distribution. Okay, now the Z-score for a 95% confidence interval is 1.96. So we can see with a larger sample size, this number gets closer to 1.96. Okay, as this gets bigger, it's going to get closer and closer to 1.96. 90% confidence interval with degrees of freedom equals 22. Okay, here it's giving us degrees of freedom, so we're not going to do -1. We're just going to go to 22 on that line there, match it up with 90%, and we get 1.717. And then lastly, 99% confidence with n equals 46. So 46 degrees of freedom. We won't find that on the table there. If we don't find it, we go to the closest one. Okay, and we just use that 2.690. Now let's do one of these confidence intervals, and this confidence interval is called a T interval. Common claim is that garlic lowers cholesterol levels. In a test of the effectiveness of garlic, 49 subjects were treated with doses of raw garlic. The changes in their levels of cholesterol have a mean of 0.4 and a standard deviation of 21. Use the sample statistic, so it's telling us this is a sample. We get n equals 49, that's our sample size. X bar, the result of a sample, and S is our sample standard deviation instead of sigma, to construct a 95% confidence interval estimate of the mean. What does the interval suggest about the effectiveness of garlic? All right, so here it is all summarized here. First question is, what is the critical value? So we're going to look up 95% in that table with 48 degrees of freedom, and we get a critical t-score of 2.009. Standard deviation, normally it has been sigma over radical n. Now we're going to use S over radical n. 21 over radical 49. Standard error, 3.0. Okay, standard error and standard deviation are really interchangeable. We call it a standard deviation. We call it a standard error when we're estimating the standard deviation with sample data. Find the margin of error. It had been a z-score times the standard deviation. Now it's just the t-score times the standard error. 2.009 times that 3.0. Margin of error is 6.027. And confidence interval is the same as it has been. Take our sample mean, add and subtract the margin of error. We get negative 5.6 to positive 6.4. Writing our sentence interpreting the interval, same as it has been. We are 95% confident that the true mean change in LDL cholesterol after using the garlic treatment lies between a drop of 5.63 and an increase of 6.43 milligrams per deciliter. What does this suggest about the effectiveness of garlic? Well, if you take garlic to lower your cholesterol level, it might drop it by 5.63 points, or it might increase it by 6.43 points. If the change was 0, it means that it didn't do anything. 0 is right in the middle of this interval. So it suggests that garlic is really not effective. It's possible there's no change at all. It's possible it helps. It's possible it hurts. We really can't tell. So moving forward, the most difficult thing for you is choosing which type of confidence interval we use on a problem. Okay, so we use a z distribution, a normal distribution. Number one, for all proportion problems. Proportion problems are never t distributions. Okay, so along with that, we use a normal distribution if we know what sigma is. Okay, but along with that, we need to meet certain requirements. Either we have to have n is greater than 30, or the population is normally distributed. T distribution is used when we don't know sigma. Okay, and again, one of those two things are met. We always need either a large enough sample size or a normally distributed population. Once we have one of those two things, we look, do we not know sigma? In this case, it's a t distribution, or do we know sigma, in which case it's a z distribution? Okay, if we have a population that's not normally distributed and their sample size is too small, we can't do a confidence interval at all. So with that said, which type of problem are these? Part A, we have n equals 9, sample mean of 75, standard deviation of the sample, S, is 15, the population has a normal distribution. This is one of the key things that we want to see. This means we can do the problem. Now we look at this, we see we only have the standard deviation of the sample. This is a t-score problem, a t distribution problem. It's okay that our sample size is small because the population has a normal distribution. Part B, n equals 5, sample mean 20, standard deviation 2. The population is very skewed. Okay, that's not good. So if it's very skewed, we look at our sample size. Is it greater than 30? It's not. Okay, we stop there. We can't do this. Right? We need one of these two things to be true, if not both. Part C, n equals 12, x bar equals 98.6, sigma equals 0.6. the population is normally distributed. Okay, so this is good. Now we look up here. We know the standard deviation of the entire population, which means we're going to use a z-score. Part D, n equals 75, sample mean 98.6, sigma 0.6, population skewed. Okay, so skewed is not good. We look at the sample size. It's above 30. That works. Sigma is known. Z-score problem. And lastly, n is 75 again. Really, as soon as we see this, we know it's doable. Okay, it doesn't matter that it's skewed down here. This time we don't know sigma. We only know the standard deviation of the sample, which makes this a t-score. Last problem, and this is not specific to t-distributions. This is true of all confidence intervals. Here we have weights of discarded garbage taken from a random sample of 62 households. We create a 95% confidence interval, and we get this interval down here. We want to use this interval to find the best point estimate and the margin of error. Anytime we have a confidence interval, whether it's a z interval or a t interval, we can get the point estimate and the margin of error very easily. So the point estimate to start is exactly in the middle of these two numbers. So if we find the midpoint of these two numbers, we find the point estimate used to create that confidence interval. Okay, so in other words, we find the result of whatever our sample was. So we just take those two numbers, we add them together, we cut it in half, and we find that they took a sample, and the result of that sample was a mean of 25.6415. The margin of error, now keep in mind this is right in the middle of these. So if we were to take either of these numbers, like 27.218, and subtract this number, we would get the margin of error. Okay, same thing if we took this number and subtracted 24.065, we would get the same number. Okay, that's one way to get the margin of error. The other way is just to find the difference between these two values. Okay, so we subtract these two and we cut it in half because one margin of error goes to the right, the other one goes to the left. We get a margin of error of 1.5765.